Okay, so for today's lesson, we're going to go over magnetism. We started covering this just before, of course, the class cancellations here, but we're going to continue going over just some of the things we had talked about. And those things are going to include magnetic fields, magnetic forces, electromagnetic induction, as well as charged particles moving in electric, magnetic, and gravitational fields. Now, as you can see on the slide right now, I'm tentatively planning a quiz for Wednesday, April 1st. It will cover those following things, of course, but the reason I say tentatively is we still don't know exactly 100% what assessment is going to look like. In other words, what are your quizzes, what are your exams going to look like? I'm pretty sure that for senior high courses, it's going to pretty much stay the same as what it usually would be, maybe just some online quizzes and stuff. But again, we'll hold off on that. I'll let you know in advance. By Monday, hopefully for sure, I'll let you know whether this quiz is going ahead. But for now, just keep that in mind. I would like that to go ahead because when, of course, classes were canceled, we were already ready to go. We didn't have to, cover any more material. Again, we've already completed this entire unit. Forces and fields is done. It was just review from here on out. If we're going to have a unit exam for this, I want that to be on Monday, April 6th. But again, that is tentative. There is no guarantee we're going to do that. I'll let you know if that changes as well. Anyway, let's get rolling here. First of all, magnetic fields. This is something that we talked about earlier on in the forces and fields unit. Magnetic fields are oriented pointing away from a north pole and towards a south pole. Okay, so kind of like when we talked about electric fields pointing away from a positive charge, magnetic fields behave in a very similar manner. They point away from the North Pole. Now, magnetic fields are denoted in an equation by the symbol B with an arrow. Let's just see if I can get my pen to work here. There we go, yeah, so B with the arrow on the top of it, that means a magnetic field. But as confusing as this sounds, the unit on that is actually in a unit called Teslas, right, with a capital T. So even though in an equation the unit is this B with an arrow, the actual unit value on it is Teslas. Now, an electric current passing through a conductor, so like a current carrying wire, is actually going to generate a magnetic field. Our first and second left-hand rules explain how this would behave. The first left-hand rule, this one right here, says that when you have a current going through a wire, so the current traveling, let's say, this way, it's going to produce a circular magnetic field going around the wire. And the way to remember this is to use your left hand and point your thumb in the direction of your electron flow, and then use your curled fingers to represent the direction of the magnetic field lines. Now, there's a second left-hand rule, which is pretty much the exact same thing, where you point your thumb out and you use your curled fingers, except for that time, it's where you have basically wires that are coiled around something. So you can see these wires circulating around this coil. Now, your curled fingers in the second left-hand rule actually represent the direction of the electron flow. So the electrons are your curled fingers in that case, and your thumb would actually represent the direction of the magnetic field. Basically, the first and second left-hand rules show the exact same thing, just in different situations. The first left-hand rule shows when you have a straight wire, and the second left-hand rule shows when you have the wire curling around something, producing, of course, a straight magnetic field. Now, with that, we also had a third left-hand rule. The third left-hand rule was actually used to determine the magnetic force. Now, magnetic force, of course, in equations was denoted by Fm, right? There were a couple different equations for it. We'll get to that in a second. They are on your formula sheet, and now might be a good time for me to tell you, if you don't have a formula sheet, I do have them posted on the Google Classroom page. You can access them that way. Now, I want you to note that a magnetic force only occurs if the velocity of the charged particle is perpendicular to the direction of the magnetic field. Okay, so let's say in this example, we can see in this picture, we have a north magnet and a south magnet. Therefore, the direction of your magnetic field is going out of the north and into the south. And the velocity of this charged electron right here is actually perpendicular to it, perpendicular being like at a 90-degree angle, right? So since that velocity is perpendicular, there is going to be a magnetic deflecting force here. Now, the force can be used by putting your hand, kind of like in this picture here, in like a straight right angle formation, and your palm actually represents the direction of the magnetic force. So your pointed fingers represent the direction of the magnetic field, your thumb represents the direction of your electrons, and then your palm represents the direction of the magnetic force. Now, something to keep in mind here is that a parallel velocity is not going to result in a deflecting force. So in other words, if you had a charged electron moving this way, like let's say from the north magnet to the south magnet, there isn't going to be a deflecting magnetic force here. There won't be any magnetic force acting on that charged particle whatsoever. If you have an oblique velocity, or in other words, where I'm from, we call that diagonal, right? An oblique velocity, so at an angle, only the perpendicular component is going to count towards the magnetic force. So when you have a problem like that, you have to break it down to a perpendicular and a parallel component, or in other words, an x and a y component. And your x component, at least in a drawing like this, would represent your perpendicular velocity. We'll do an example like that in a question. That might be a lot to absorb right now. Let's just get to an example here. So first example right off the bat here is, suppose a north pole of a magnet is placed 20 centimeters above a south pole of another magnet. It says magnetic for some reason. Let's just cross that out. Anyway, the uniform magnetic field between them has a strength of 0.250 Teslas, right? So that's your magnetic field strength. A beam of electrons is shot into this region at a velocity of this many meters per second at an angle of 10 degrees up of right. So in other words, we have an oblique velocity here. Might be useful to note that. What we're looking for is the magnetic force. All right, if you look on your formula sheet, you can actually see there's two different formulas for magnetic force. I'll just write them at the top here so they're out of our way. The first one is F, or I should say Fm, equals Q V perpendicular, B with an arrow. But the other one that's on your formula sheet is Fm equals I L perpendicular, B with the arrow. These two formulas pretty much mean the exact same thing. They're both going to be used to find your magnetic force. The only difference is that this one, QVB, is referring to the charge of one specific object and the velocity perpendicular of also that one specific object. The other magnetic force formula is used for when you have a wire, right? Some sort of current carrying conductor. And the reason I know this is not only this I right here, the I actually represents the current flowing through the wire, and that's measured in amps. But this L is the dead giveaway. The L represents the length of the wire in the magnetic field perpendicular, that's what the little perpendicular sign means, perpendicular to the magnetic field. Long story short, you use this one on the left if you have a single particle or a beam of particles, and you use this one on the right if you have a wire, okay? Since we have a beam of electrons, we're going to be using the big one here on the left, right? So since we know we're going to have to use the formula Fm equals Q V perpendicular B with the arrow, let's just take a little test here and see what we actually already know. Well, first thing in this question, we know the strength of the magnetic field. So we know B. B is all established, right? We kind of know the velocity, but notice this velocity is an oblique velocity. It's not actually the velocity perpendicular. That's where we're going to have to break it down into a perpendicular velocity. I'll show you that in a second. The last thing here is Q in this equation. So Q, of course, is your charge. Since it's a beam of electrons, if we just thought of one electron at a time, we actually know the charge of that. Q, in case you've forgotten, is the elementary charge when it's an electron. It's 1.60 times 10 to the negative 19 coulombs. Okay, so we know Q, we know B, we don't quite know V perpendicular, but we can find it. Let me just draw a picture real quick of what's happening here. We have our north magnet, and it's 20 centimeters above a south magnet. And I apologize for my drawing here. I'm drawing with that trackpad pen thing that I have, and it's not exactly the best. But anyway, and then you have your beam of electrons shot into the region at a velocity of 10 degrees up of right. Well, remember when we draw something like up of right, I would start by drawing something straight to the right, and then something up, because it's up of right, so go right first, then up. And then your true velocity here is that angle, and we know the angle is 10 degrees, and the magnitude of that is 2.50 times 10 to the 5 meters per second. Again, I apologize for it not being super clear. I'll keep practicing on this one. It's harder than it looks. Anyway, so what we notice here is that oblique velocity is not the actual velocity that'll be useful in this. We want to find that velocity perpendicular. Perpendicular, again, means at a right angle compared to the rest. So we're really looking for this piece right here. That would be V perpendicular. Notice in this triangle here, that would be our adjacent side. So our adjacent side, we have our hypotenuse. By just normal trigonometric functions, adjacent and hypotenuse are both used in cosine. So we can set this up as cosine 10 degrees equals adjacent, which is V perpendicular, over your hypotenuse, which is that 2.50 times 10 to the 5. And then, of course, just multiply that 2.50 times 10 to the 5 over. Make sure you're in degree mode in your calculator. I've already done this, so I will just tell you the number. I get V perpendicular equals, and I'm going to keep all the numbers I can here realistically. It's quite a big one, 246,201.9 meters per second. Okay? I'm keeping all those numbers because I want to keep my answer as accurate as possible. This isn't my final answer. I'm not going to round to significant digits yet, so we'll leave that where it is. Anyway, from here, we now have V perpendicular. We had Q, we had B, so we have all three of those things in that formula. So I can take this and say Fm equals Q, which we know is 1.60 times 10 to the negative 19, times V perpendicular, which we just found to be 246,201.9, and then times B, which was actually given to us in the question as being 0.250. Throw that in your calculator, round to, I guess looking at our question here, we have 3 sig digs is what we're going to have to deal with here. So round it to 3 sig digs, what I got was 9.85 times 10 to the negative 15 newtons. Perfect. All right, next example. So in this next example, we have a 50 centimeter long wire. That's going to be useful. It's perpendicular to a downward magnetic field, and it has a current of 0.750 amps run through it. And we notice it's deflected by a force of 22.0 newtons. Find the magnetic field strength. All right, so the magnetic field strength, that's your B with an arrow. We know our magnetic force. We know it's a wire. Pretty clear now. We should know that our formula we use is Fm equals I, L perpendicular, B with an arrow. Okay, so we want B with an arrow. Notice we have our magnetic force. We actually also have I again is your current, we have that. And we also have the length of our wire perpendicular. It actually gave this all to us. Now the only trick here, of course, is the length of the wire shouldn't be in centimeters, it should be in meters, but that's easy enough to convert. You just divide it by 100. That gives us 0.500 meters. Anyway, let's throw our numbers into this formula that I put up here. Fm, of course, is 22.0. That equals I, which is 0.750, times L perpendicular, which is 0.500, and B with an arrow is what we're looking for. To find B with an arrow, just divide these other two things over to the other side. I've already done it, so I'll just tell you the answer. B with an arrow, in other words, our magnetic field strength, I probably should call it what it actually is here, rounded to 3 sig digs is 58.7, and the units on a magnetic field strength are, of course, Teslas. So that would be the answer to that question. All right, next up, electromagnetic induction. This was quite a weird concept that we covered. It comes from something called Lenz's Law. Lenz's Law states that the direction of a magnetically induced current is such as to oppose the cause of the current. In absolute plain English here, if you have a coil of wire, let's get the pen back here. If you have a coil of wire and you bring a magnet into it, that coil of wire is going to have an induced magnetic field that opposes whatever magnet you're trying to put into it. So in this picture here on the left, we have a north end of a magnet being moved towards this coil of wire. It doesn't want that to happen. Remember, a north end of a magnet is going to oppose another north end of a magnet. So in other words, what this coil of wire does is it induces a magnetic field inside of it so that there's a north end here to oppose this north end, and therefore a south end over here. Now, by our left-hand rules, the first and second left-hand rules, since we have a magnetic field going outwards this way, you can use your thumb to point your thumb to the right, of course, using your left hand, and you'll notice that your fingers curl over this way. So what that means is, inside this coil of wire, when you bring a magnet with a north end towards it from the right here, you're going to have your electrons coiling over the wire that way, right? Now, likewise, if we went the other way around, if you had your north end of your magnet and you were trying to remove it from the coil of wire, so like in this right picture here, then it's also going to try to oppose that as well. So it's like the coil of wire really doesn't know what it wants. It's just trying to always oppose whatever the magnet's trying to do. So if this magnet's trying to get out of here and it's trying to move away from the coil of wire wants to wants to oppose whatever that's doing, right? So in other words, once you start trying to remove the magnet, the coil of wire says, no, actually I want the magnet back in. And the thing that's going to try to pull a magnet with a north end back in is of course putting a south end here because they'll be attracted, and therefore a north end on this end. Likewise, use your first or second left-hand rule again to show that your thumb points this way. You're going to notice your fingers curl towards you. So this time, when you try to remove this magnet from this side, you're going to notice your electrons moving over and above the coil that way. Now in class, when I first introduced this, there was some digital application I was trying to show you guys, but it wasn't working on the computer. I finally managed to get it to work. Let's see if I can actually share it with you here. There's going to be two little things I show you here. The first one is, of course, we have a coil of wire, and we have a magnet with the north end here on the right side. What I want you to note while I do this is I want you to watch where these little blue dots inside the coil of wire go. Now those blue dots are going to represent electrons. So again, we're going to use our left-hand rule to show the flow of these electrons. If I take my magnet and I start moving it towards the coil of wire, notice that those electrons start moving down. Now I'll do it again really slowly here. If I move the magnet, the north end of the magnet, towards the coil of wire, the electrons start moving downwards. Now again, what that's really doing is the coil of wire is trying to oppose the motion of that magnet. So in other words, when I try to pull this in towards, it's going to be putting a north end here and a south end over here. So the north end on this side, of course, is going to produce a magnetic field pointing to the left, which if you use your fingers with your first and left hand rules, you're going to see your fingers are curling over above the coil of wire. Therefore, your electrons should be moving down. As we can see, they do try to move down. Now, you're also probably noting that when I have the magnet in here and I try to remove it, they move back up, right? So if I do that again, they're going to try to move back up. This is because, once again, it's opposing the motion of the magnet. It would be producing a south end on this left-hand side and a north end on the right-hand side. Using your left-hand rules, you can see it would coil over the wire in that situation. Now, you're also probably noticing this little light bulb on here. What this is really showing is, of course, when you have an alternating current going back and forth, that motion of electrons is actually going to be what powers the light bulb up on top. So if I move this back and forth, the light bulb turns on to various extents, right? Now, the other thing I wanted to show you in this is another app that they use called a generator. Basically, how a generator works is getting some sort of a magnet to rotate near a coil of wire, which induces a magnetic field and then gets those electrons to flow. So how this is going to work is I actually, instead of having a light bulb, I've set it up so that there's a voltage meter up here. You're going to see how the voltage will bounce back and forth once this magnet starts rotating and changing the magnetic flux, is what we call it, inside this region. So if I turn on this tap, you're going to see as this magnet rotates, these electrons bounce back and forth and back and forth. That, of course, produces an alternating current where you're going from a positive to a negative and back. And that's kind of just basically how generators work. Anyway, I'll put that away. We'll move on to the next thing here. We're almost done. Charged particles in various fields. What I want you to remember is that a charged particle of any significant mass, so basically anything larger than basic particles like electrons, protons, alpha particles, etc., they're also going to be impacted by gravity, right? If you're just dealing with an electron or just dealing with a proton, you don't have to worry about gravity because gravity's influence on those very, very small particles isn't really going to matter. Now, gravity, though, on these larger particles, like when we saw Millikan's oil drop experiment, gravity might actually combine with the electric force and or the magnetic force. You have to look at a whole situation, an entire problem, and figure out what kind of forces are actually present in any of these problems. So I want you to be mindful of these situations, as you'll often need to find or use the net force to solve these problems. You won't always have to do that, of course. You can also, like, sometimes just connect your forces and say they're equal, especially if the question says that the object is suspended, which would mean you have balanced forces. But you also should keep in mind the direction that these forces will point. I can ramble on about this for like an hour. Instead, I think it'd be way easier if we just did a question. So here's an example where we have a 500 milligram charged oil droplet that is suspended between two parallel plates, okay? What you might remember, it's been a while, I know, but parallel plates will actually produce a uniform magnetic field, or sorry, electric field in between. So in other words, everywhere in between two parallel charged plates, the electric field is the exact same magnitude the whole way through. Now in this question, it's telling us the top plate is positive, so we can assume the bottom plate, of course, is negative. That means I guess my arrows really should be pointing the other way in this case, because remember in an electric field, your arrows are drawn away from the positive towards a negative. So my arrows would actually technically go this way, just for correctness. Anyway, the voltage between the two plates is 75.0 volts, and the plates are 0.100 meters apart. Find the charge of the oil droplet. There's a lot going on in this question. First of all, the only kind of forces that are going to be present here are, of course, your electric force, because you have charged parallel plates, but also because it's a reasonably massive, quote unquote, oil droplet. We also know gravity, Fg, is going to be playing a role in this as well. Since we also know that this is suspended, we can therefore assume that Fe, your electric force, is going to equal your Fg, your gravitational force. Those two forces are going to be balanced out. The force of gravity pulling it down will equal the force electric pulling it back up. That's what's making it suspended. That's why it's just hovering in place. What might be useful here is looking at the formulas for both Fe and Fg. If you look on your formula sheet, Fe actually only has two different formulas. There's one really big one, kq1q2 over r squared. Kind of looks like that law of universal gravitation that we looked at in physics 20. That's only the electric force when you have two different charged objects. The other electric force formula is going to be a lot better here. The other electric force formula, of course, says Fe equals E with an arrow, that's your electric field strength, of course, times Q, which would be the charge of your object. Fg, on the other hand, Fg's formula is pretty familiar to us. It's just mass times 9.81. So if we throw all this information in here, you're going to see that Fe equals Fg can actually be written as E with the arrow, your electric field strength, times Q, your charge, equals the mass times gravity, or 9.81, right? We already know gravity, 9.81 is pretty clear. We know the mass, it's just in milligrams. Remember, mass should always be in kilograms. We'll convert that in a second though, so I'll say we have that. We're looking for Q. Q is the charge of the oil droplet, so that's what we're really looking for here. And E with an arrow, though, we don't actually have. Maybe a starting point for us then would be to find the E with the arrow, the electric field strength first. And again, if you have a look at your formula sheet, you can actually see there's a couple different places where the E with the arrow, so your electric field strength, actually shows up. But the one that's going to be pertinent to us is the one that says E with an arrow, electric field strength, equals your voltage divided by your distance. This is usually a good starting point whenever you have parallel plate questions. If you have parallel plate questions, finding that electric field strength is critical because, like I mentioned earlier, it is uniform. It is the same in the entire region between those two parallel plates. We have our voltage, 75.0 volts, it's right in the question. And we actually have the distance as well. The distance the plates are apart is just 0.1 meters. So we can find the electric field strength, no problem here. So electric field strength, therefore, equals 75.0 divided by 0.100, and that's again volts divided by meters. That gives us 750, and the units on electric field strength are just, well, volts per meters. Sometimes for electric field strength, we use newtons per coulomb, but in this case, maybe volts per meter might be a little easier to wrap our head around. So that's fine. So now we have our electric field strength, E with the arrow. We're looking for Q. We kind of know our mass. Maybe we should deal with that right next, but we also know our gravity. So you know what? Let's deal with that mass. Our mass that we had was 500 milligrams. Milligrams aren't a good unit though. We don't like using that. So let's first change that to grams. Remember, to go from milligrams to grams, you got to divide that by 1,000. So that tells us we have 0.500 grams, or in other words, half a gram. But also remember that for whatever reason in physics, we actually consider kilograms to be the basic unit of mass, right? So in other words, we can't just keep 0.500 grams. We actually have to change that to kilograms. And remember, to go from grams to kilograms, you also divide that by 1,000. So what I got for my mass, if you divide that all through, is 0.0005 kilograms. And you could also say that that's 5 times 10 to the negative 4 kilograms if you prefer using that, whatever floats your boat. Either way, though, we now have all of our units in this equation, so we can actually solve this. Let's throw our numbers in here. So E with the arrow, the electric field strength, is 750 times by Q, that's what we're looking for, that would be the charge of the oil droplet, equals mass, which is 0.0005, times by gravity, which is 9.81. Multiply these two things together on this side and then divide by 750. Then you can round your answer to, looking at the question, it looks like 3 significant digits. So we have got 6.54 times 10 to the negative 6. And of course, charge is measured in coulombs. But wait a second. There's one more thing I'd like to do on this question. Charge of an oil droplet is not just a magnitude. It's also nice to know if it's a positive charge or a negative charge. Going back to the diagram that I drew up in this top corner here, you can actually see that the top plate is positive and the bottom plate is negative. In terms of electricity here, it's being attracted to the positive plate. If this charged particle is attracted to something that's positive, that would imply that the charged particle itself must be negative. So just to make this answer more complete, I'm going to say it's negative 6.54 times 10 to the negative 6 coulombs, and that would make it a more complete answer. Okay? Anyway, that's it for the lesson. Hopefully we didn't go too long here. It looks like it was over 20 minutes for sure. Apologize for that, but hey, you know what? Not too bad for a first lesson. For practice, I want you to continue working on that homework assignment. I gave it out before the school cancellations all came down, right? But I will say for now, this is now due on April 1st. Again, if that changes, I will let you know. We don't fully know what assessment looks like here, but since we were already working on it, I think it would be a reasonable expectation just to continue working on it. If you lost it, there is a digital copy available on Google Classroom, in case you've misplaced yours, of course. To submit this assignment, what I'm going to tell you just for now, because ideally we would want to submit this digitally, take clear photos of each page and then upload them to Google Classroom. So go on where the assignment is posted on Google Classroom and upload each clear photo of each page to Google Classroom on that. Now, if you have a scanner at home, that's probably going to be even easier for you. Just scan each page and then upload it that way. But regardless of how you upload it, make sure that everything in the digital document you submit is easily readable. Now, if you can't, for whatever reason, do this, if you can't submit photos, if you can't scan anything like that, if that's going to be a problem for you, you need to send me an email as soon as possible. We'll try to figure something out. And again, if this whole April 1st deadline thing changes, I will let you know. Just keep your eyes on Google Classroom. I'll make it very clear for you. If you don't want to work on your homework assignment, or if you're already done, make sure you finish any of the practice problems that you haven't completed in your notebooklet already. There is a digital copy of the notebooklet posted on Google Classroom as well. That's up to you. And then just another reminder, just to leave you here tomorrow. That's on Friday the 27th. We're going to have a Zoom conference between 1 p.m. and 1:30 p.m. So in other words, be there just before 1 o'clock. Try to be on like by 12:57, 12:58 or so, because we're going to start right at 1 o'clock. To get on Zoom conference, again, go on Google Classroom. The information's all there. I'm not going to post it in this video because I don't want that floating around, but that is when our Zoom conference is going to be. And the only thing I ask of you is to be prepared, to ask me some questions either from the notebooklet or from the homework. That's what that Zoom conference is going to be all about. You'll ask me a question, I'll walk through it. That's about it. Okay? Anyway, if you have any other questions, let me know in advance. You can send me an email. You can post it on Google Classroom, whatever you need to do. Thanks so much, guys.